Transposing a matrix, swapping its rows with its columns, is often taught as a simple spreadsheet operation. However, this physical grid flip is the shadow of a deeper geometric reality. To understand the mechanism behind this operation, we turn to the rigorous foundation established by Kenneth Hoffman and Ray Kunze in their text Linear Algebra. This text has defined the mathematics curriculum at MIT for decades, prioritizing abstract conceptual clarity over rote computation. When we execute that matrix flip, what geometric transformation are we actually describing? Standard vector spaces cannot answer this. We must build a new theoretical framework to see the transformation's true form. We must leave the familiar grid and enter the dual space. Consider a vector space, V. A linear functional is a specific transformation, F, that maps vectors from V down to a single value on the one-dimensional scalar field, F. To these linear, F must strictly preserve the rules of additivity and scalar multiplication. There isn't just one such functional. If we collect every possible linear functional that can operate on V, we find they form a vector space of their own. This is V star, the dual space. Here, the vectors are the linear functionals themselves. Every target vector space, like W, possesses its own corresponding dual space, W star. These dual spaces act as a parallel mathematical reality, providing the infrastructure required to define the abstract transpose. Let T be a standard linear transformation that maps vectors from space V into target space W. This transformation naturally induces a mapping between the two corresponding dual spaces. This induced mapping operates in reverse, pulling information from W star back to V star. This is the transpose of T. It is defined by the relationship the transpose of T applied to a functional G, evaluated at alpha, equals G evaluated at T of alpha. This means applying a functional to a transformed vector is identical to applying the transpose transformation to the functional first. Hoffman and Kunze's Theorem 21 proves that this relationship uniquely and perfectly defines the linear transformation T transpose. The abstract transpose functions as a translator, taking the rules from the target space and moving them backward into the language of the domain. This transpose mapping possesses its own null space inside W star, containing all the functionals that map to 0. We can connect this abstract null space to the physical range of the original transformation, T. Theorem 22 demonstrates that the null space of T transpose is exactly the annihilator of the range of T. If a functional maps every vector in the target range to 0, it belongs in that transpose's null space. Because the null space and the range are mathematically tethered, their dimensional sizes are linked. This results in a critical identity. The rank of T is exactly equal to the rank of T transpose. The size of a transformation's output is a geometric property that remains preserved when mirrored in the dual space. How do we translate these abstract geometric mappings into coordinate-based mechanics? We represent the transformation T as a matrix, A, relative to specific bases. Theorem 23 proves that the matrix representing T transpose is A transpose. Here, the entries flip indices. Row I, column J moves to row J, column I. This index swap is the coordinate calculus required to execute the mapping from W star back to V star. Swapping rows and columns is the physical mechanism for moving information backward through the dual space. Consider one of the most significant symmetries in linear algebra, the fact that a matrice's row rank is always equal to its column rank. We prove this using the dual space framework. First, the column rank of matrix A is the rank of transformation T. Second, by Theorem 23, the transpose mapping is matrix A transpose. Third, the column rank of A transpose is the rank of T transpose. Crucially, the column rank of the transposed matrix is the row rank of the original matrix A. Finally, applying Theorem 22, the rank of T equals the rank of T transpose. Since the abstract ranks are equal, the row rank must equal the column rank. The journey into the dual space provides the structural proof for a property that often feels coincidental in basic arithmetic. We have established that the transpose is a linear mapping operating within the dual space, pulling functionals backward from target to domain. It is a coordinate-free definition that holds regardless of the specific numbers in a grid. The matrix transpose is merely the coordinate representation of this abstract process. This approach utilizes the internal architecture of linear transformations to explain the necessary symmetry between rows and columns. This structural method provides a level of clarity that brute force algebraic calculations cannot match. To see more deep dives into the logic of Hoffman and Kunze, like this video and subscribe. Real mathematical understanding comes from looking past the symbols to the invisible structures they represent.